Swayam Prabha. Digital India. Educated India.
Relatively long break. Get started again. So that's good. Hope the things that we discussed you were able to kind of reflect upon. So we were in a position where we want to effectively introduce system path interactions, relaxation, dissipation terms in the system. And as I said earlier, I'm going to talk about two primary relaxation channels which are kind of ubiquitous in spectroscopy. One is basically an excited state relaxing to ground state by emission of photon. So you have some ground state, some excited state, this comes back by emitting photon, and this is what is referred to as, know this, spontaneous emission. Now if we think of spontaneous emission, as I already kind of mentioned to you, in this case, system is of course our quantum system, and the bath is the vacuum, photon vacuum into which it can couple to, right, with all its degree of freedom. So I could kind of think of, if I were to write down my system bath Hamiltonian without interaction with a light driving force, then my thing will have my system, which is H naught, my bath, and some system bath term, and your H naught we know is H cross omega naught over 2 sigma z. Your bath, of course, is sum of all possible photon modes, where AKs are photon radiation annihilation operators. System bath coupling can be written as something like this: some coupling parameter Gk, K is for all spatial modes, a raising operator followed by annihilation of the photon, or you can also have lowering operator with creation of a photon. That's your system bath coupling. So this kind of Hamiltonian is widely known as the Jaynes-Cummings Hamiltonian, or Jaynes-Cummings-like interaction between system and bath. So the way to think about this is that I have my excitation, and the system has access to this infinite number of photon modes, which are all empty. They're all in vacuum because they're not occupied. And now my system can relax by an interaction, and this interaction given by this Jaynes-Cummings interaction, where my system gets lowered, sigma minus, and a photon is created. But of course, I can have exactly opposite process happening. I could have an absorption event happening, right? I can have annihilation of the photon and the raising of my quantum state of my system. So that's what is captured by the Jaynes-Cummings Hamiltonian. Okay, cool. So now from this kind of picture, we should be able to write down this term here. At the end, what matters for us is to understand what is the functional form of this dissipation term. Now, I'm not going to derive this or show this, but I'm going to state this. If you're interested, I can refer you to more advanced texts in this context. This is what is referred to as Lindblad dynamics or Lindblad approach. So you can kind of capture dissipation channels by what are called collapse or Lindblad operators. Lindblad operators, in which case your dissipation term in your equation of motion, one equation, these are capital L. If I'm able to define this Lindblad operator, then I should be able to write the dissipation term in the equation of motion to be this. Very messy here, precise. Okay, so in the case of spontaneous emission, for spontaneous emission, it can be shown that the Lindblad operator for spontaneous emission is given by this. Of course, it's Lindblad operator for this kind of makes sense, is a lowering operator. Okay, and this gamma here is proportional to decay rate, or the inverse of the lifetime of the state. Okay, that's your Lindblad operator for spontaneous emission. So you could have this relaxation, spontaneous emission, but this is not the only dissipation channel one needs to consider. Always remember this picture in a coherent experiment. What you are doing is you have an ensemble of chromophores. Always remember this. An ensemble of chromophores. You're coming with an electromagnetic field. The spot size is huge, right? So you're going to excite, I don't know, 10 power 18 per centimeter cube of chromophores. Okay, and because you're driving them coherently, that's at least our hope, we drive them coherently, they're all going to oscillate coherently, right? So, of course, at some point, they'll all stop oscillating because they would have relaxed the ground state. That's not the only dissipation channel, because what you're also measuring is a coherent response. Later on, we will see that this coherent oscillation going back and forth is going to generate, by electromagnetic theory, radiation, which is what you're going to observe. Now, if I'm not having this coherent oscillation, each one doing its own thing, basically each dipole is going to generate some electromagnetic wave, which is going to destructively interfere with something else, and you'll get nothing out. So you not only, for coherent response particularly, you not only want your excited state to be active, which means it's not decayed by the ground state, but also your coherence is preserved. That's a very important thing. So in your equation of motion, thus, you have to introduce a possibility for this defacing dynamics, right? Now, what is this origin of defacing dynamics? So defacing dynamics can be thought about like there are chromophores, each at different location, each interacting with its surrounding slightly differently, right? Which means that it could be undergoing small little inelastic scattering, which means the energy of that state is going up and down because it's interacting. If I take an average of all those ensemble of excitations, nothing happens. It's cool. It's not, because one goes up, one goes down. By stochasticity of the process, average will be there. But if I look carefully, each one is undergoing some random fluctuations. Okay, and that can be captured. So, in fact, maybe not tomorrow, but the day after tomorrow, we will develop a microscopic theory for this random fluctuations driving defacing. This is called Kubo-Anderson theory. At least we will not go into too much detail, but at least get a brief introduction to Kubo-Anderson theory. It's kind of deeply rooted in Brownian motion, which you all kind of aware of, the stochasticity process. But for now, what I'm going to write down is that for what we call as pure defacing. What is impure defacing? There is no impure defacing. There is also some inhomogeneous broadening, which we'll talk about later. The Lindblad operator for that is some gamma percent phi, meaning that's a phase scrambling happening, between different oscillators with again my polymeters. If you think about this, if I take this Lindblad operator, put it back here, you will have a term of this kind. If I substitute in this, you'll get it. Basically, you can show that this is flipping coherence. So it's adding phase randomly. Okay. The important thing here is that for pure dephasing, diagonal of my density matrix is preserved, which means there is no loss in population. Whereas spontaneous emission, you will have loss in population. But for dephasing, population remains stationary. Now, if I take these two terms, put it in this into this dissipation term and write it, you don't need to worry about it because it's a bit more involved. But I want to focus on the final part that we will get. Basically, you take these two, put in this, and then write the equation of motion. Let's write down the dissipate term. Will be capital gamma 2 to sigma rho sigma minus sigma plus minus bracket plus z rho z minus rho. So you can see there is one term which is adding dissipation as a lifetime, another term which is dephasing, a dephasing rate or emission rate. Okay, which if you think about it, we have already kind of guessed or intuitively guessed that we will have a term of this kind, right? Some gamma over term or which kind of, if I put it back in my differential equation, it will correspond to a simple exponential, mono-exponential decay of whatever coherence or the population that I'm looking at. And in fact, more elaborate microscopic kind of theory can also give similar kind of framework. Okay, so now I want to write down optical Bloch equations in this context. Again, I'm not going to solve this because I'm not going to gain anything by solving this. Q-tip will do this for us, so we don't need to worry about writing down explicitly. But for the sake of instruction, let's just write down a couple of those equations. Let's say we take excited state population. Excited state population will be, which term should be this for excited state population?
1
1 will be minus gamma 1 1 I 1 0 0 1. This is population economics. And if I take one of the off diagonal terms, let's say I take 0 1 construction, you see I delta 2 gamma 5 this is coherence. Remember, this is derived by plugging in this equation into the optical equation of motion and doing the optical block equations. Okay. Now what you can see again here is, okay, what parts of this equation that impresses you the most? Anything that you look at it and say, oh yeah, it makes sense. This is what is expected.
Decay and excited state depends on the population.
That's very good. So you look at the first equation, population dynamics, it only has capital gamma, spontaneous emission rate, right? There's also this I sigma term here, I omega term here, which relates of course to coherence. So there is one component here which simply tells my population will decay exponentially. But in condition where my light matter coupling is strong, or resonance driving is strong enough, which is given by the Rabi frequency here, then I could have an oscillatory term in the population. You agree with me on that, right? And as we kind of already seen, dephasing or decoherence process has no significance in the dynamics of the population. It doesn't matter. You agree with me on that? Right? Now, on the other hand, if you look at the second equation, there is an oscillator term here. There is also oscillator term here with some dephasing, damping here. Damping given by small gamma as well as the spontaneous emission rate. Both of them contribute to your coherence decay. So even in the absence of any dephasing process, eventually my system or coherence will decay simply because my population has decayed. Kind of makes sense. Because spontaneous emission is going to be there. I am going to be in contact because of the nature of the system, light matter coupling. I'm always going to be in contact with my bath of photons. So spontaneous emission rate is going to be an intrinsic property given to you, even if you kind of magically cut off any kind of dephasing process. So everything will have a finite lifetime. You cannot get over that, right? So that will contribute to coherence decay. So even if I don't have any dephasing process, over a period of time, it will stop oscillating simply because you have population loss, right? On the other hand, you can have additional contribution because of this noise fluctuations quantified by my lowercase gamma. I think it's more than trying to understand it, how these equations have come about. It's important to kind of get a physical intuition of what this means, which kind of relates back to the physical observables that we will measure. Now let's take a special case now. Let's take these two equations. Let us look for steady state solution.
There is decoherence and phasing too, right? Can we
Yeah.
use the two from this?
Yeah, so decoherence will have both contributions from dephasing and the lifetime. So if I plot this, it is going to be oscillating and it's going to die down. And this thing will have contribution from gamma as well as sometimes in the language of spectroscopy, this is sometimes called as tau 1 and this is tau 2. And this is your dephasing rate because of interaction with the bath, which is not photon, everything else because energy fluctuations. This is simply the lifetime. And coherence decay will have both. Now, in most realistic systems, especially dirty systems that I work with, the dephasing dynamics are so much faster than lifetimes that most often the killer for decoherence is dephasing and not lifetime. And I say dirty is because it's interacting with everything around. Okay, let's go and try to find steady state solution. So when a steady state solution, you are continuously driving the system, so much so that your rho 1 1 1 are all stationary. So if I substitute that in both the equations, this will be 0 equal to minus gamma 1 steady state plus I omega 0 steady state 1 steady state. Second equation will become I delta plus gamma 2 1 steady state plus I omega 1 state plus 1. Okay, looks cumbersome, but you can kind of reorganize this, substitute for one to get the other. So I'm going to write, for now, let's say I'm looking only at steady state, excited state population, that are 1, 1, steady state. If I write this, I will get what does this look like? Functional form? Lorentzian. Lorentzian keeps haunting us in this course. It's a Lorentzian. But Lorentzian corresponding to an excited state population. What will be the spectroscopic observable which gives you access to that? To an excited state population, steady state excited state population. You can take wild guess, it's fine. What could be a spectroscopic observable where you're driving the system continuously and the spectroscopic observable is able to gauge how much excited state is there? Absorption, you're looking at not excited state population, you're looking at only coherence between ground and state. Spontaneous emission. Fluorescence. Photoexcite, it will emit light. And that emission of light is going to be proportional to the population which is existing. So if I measure in principle resonance fluorescence, of course you're driving in resonance, there's an assumption, driving in resonance, you're going to get a Lorentzian, and that Lorentzian line width is going to depend on, most importantly, it's going to depend on these parameters here. Of course, it will be centered around delta, your detuning. Remember, you are in the rotating frame, which means you're shifted by plus omega, so you're in rotating frame. So you're going to be centered around delta, your detuning, between the energy difference between your two things. Spectroscopically, you're going to be at the energy of whatever state is, but in formalism, you are going to come there. But the effective line width will be effective line width of this Lorentzian of the resonance fluorescence will be capital gamma over 2 plus the square. So it's going to depend on the lifetime, on the defacing, and the Rabi frequency. It is very common, especially in the contemporary research, because everybody can easily do photoluminescence. It's very easy that you take a material, you measure photoluminescence, and you say this line width, it may not even be Lorentzian, but let's say it's Lorentzian. And let's say you want to measure electron phonon coupling in the system, or system bar interaction, whatever. Here you are assuming that all your defacing is happening because of interaction with the phonons. So it's very common for people to do, basically measure this line width as a function, this line width, full width of maximum, line width as a function of temperature, for example, and they will say that this line width is increasing in fluorescence. That's because as you increase the temperature, you're populating your bath, the phonon bath, which is able to scatter and couple with your thing. So you're adding this, you're increasing this defacing term. Okay, and so you're kind of saying, okay, if I measure the line width of simple experiment called resonance fluorescence, I can get access to defacing. Okay, the problem here is that you're completely forgetting that there is spontaneous emission intrinsically there. You're forgetting there is Rabi frequency there. More importantly, you're assuming that your line width is Lorentzian. Okay, if you have done photoluminescence, especially of many material systems, it will seldom be Lorentzian. It will be a Gaussian. The reason it's going to be Gaussian is because you not only have what we call as pure defacing, but also have additional contribution called inhomogeneous broadening, which could also be evolving with temperature. Because of this reason, whatever estimates you get by simply doing resonance fluorescence and temperature dependence, line width analysis, and then saying, I know electron phonon coupling parameter, is most often inaccurate. It is at best a upper limit of the estimation. Okay. In fact, hopefully in the course I will demonstrate that we can separate this out in 2D spectra. In 2D spectra, unlike resonance fluorescence, you can separate out homogeneous line width or pure defacing from inhomogeneous broadening. The Gaussian and Lorentzian can be separated out, which is something that we will see, hopefully.
What exactly do you mean by inhomogeneous broadening?
Inhomogeneous broadening basically comes from, okay, in a very simple sense, materials are not ideal. And so you can have chromophores, each part having slightly different energies fundamentally. Think of it like you have the center omega naught itself having a distribution. So your photoluminescence is going to be a bunch of Lorentzians which are overlapping. Okay, and this is your line width which will give you this, but what you are measuring is this. Okay. I'm not saying this should not be used, I'm just saying that caution has to be put when to kind of say, okay, this is really an accurate estimation. The answer is most likely not. Okay, so steady state is easy to do. What we are interested in some kind of dynamics now, right? Some kind of dynamics. So to do that, let's try to use Q-tip. Before doing that, what I want to kind of demonstrate to you are transient population dynamics. Ground or excited state, we can choose. But I'm going to assume some things. I'm going to say my delta is 0. So why not? I want to keep it simple. Retuning is 0. And since I'm only interested in population dynamics, I want to simplify my life further. Let's say my defacing is 0. Of course, it's never 0, but let's put it that way. Okay. Now I'm already going to allude to you something. So there are two important parameters left out, which are capital gamma, spontaneous decay rate, and your Rabi frequency. So depending on the relationship or the relative amplitude of these parameters, you can get 3 different kind of regimes possible. Remember, already in the equation we already intuitively found out there is some kind of decay happening, and there is also possibly some oscillation happening. Now, the relative weight of this is determined by the relative weight of these two components. Now, if I have my Rabi frequency much less than gamma, then your decay will be dominating. So then your population dynamic, let's say dynamics is going to be mono exponential. On the other hand, you come with a very strong electric field, okay, or you have a very strong dipole moment in the system, or a combination of both. Then your Rabi frequency is much larger than spontaneous decay rate. Okay, so then your population dynamics will have very fast oscillations and weak, very fast coherent drive or oscillations and weak damping. If you are in between, then you'll have what is called underdamped oscillations, sometimes referred to as Rabi flops. Okay, now let's start doing Q-tip. Okay, so we want to be able to kind of get this kind of behavior. Okay, we want to be able to see mono-exponential, underdamped oscillations are fast, coherent, one of them, right, or three of them. So let's do that. Let me share my screen here. Yeah, sure.
Even in the third case, when it is oscillating,
It will go down.
envelope will rise.
Yeah, it will go down. It's not. There is interaction still. It's not going up. It will damp down. Okay, good. Okay, let's start. I will share these notebooks with you. I kind of did it on Colab, so I can kind of share it with you. Can you all see it, or can I zoom in? Okay, so this is all in Colab. You could use Colab if you want. The only thing is you need to pip install Q-tip on Colab too every time you do it. It will not take much time, but you have to do it. Otherwise, Colab has nothing. So here, our simulation. It's momentous occasion, so all right. So what we are doing is it's a two-level system, and we are assuming that it's already excited. Okay, it's already excited under the influence of some coherent drive, and there is some spontaneous emission. Okay, that's our goal. So some important packages, we need to have NumPy, PyPlot, of course. You can import everything from Q-tip. In this case, I imported basis, sigma, p, sigma, m, and mesol. I'm going to go through that, each of them separately. Q-tip has better, okay, good. So first, let's put system parameters. System parameters only two: decay rate and Rabi, right? Here I'm kind of putting a Rabi list because I want to see what happens if I change the Rabi frequency, right? So I have a list here, choose 3, you can choose how many you want, and I choose a time grid, okay? Because I want to eventually calculate time dynamics from time grid. So these are my system parameters. Now comes the important part. I need to be able to define my basis, my quantum state, as well as my operators. So the thing I want to start out with is that I want to be in the excited state, right? I want to be in the excited state. Two-level system. So this function basis allows you to do that. So basis do with my system on the excited state. Okay, that's what this excited tells you. It's basically defining my excited state. My raising and lowering operators, sigma plus and sigma minus, Q-tip has inbuilt functions, sigma m and sigma p. You can directly use it. Okay, should I make it even bigger? See, that's the reason I kind of went to the trouble of going through this formalism, because that is exactly transferable to Q-tip. So it kind of works in that space. So it's kind of easy. Okay, now we need to still start with a density matrix. Okay, here I am only defined my state, which is a column vector. My state, I'm developing it from my excited state. So excited state multiplied by the excited state dagger. So then you'll get a 2 by 2 matrix given by this. Okay, so I have defined my basis and operators. I have defined my initial state. Is everybody okay with this? Fine? Good. Now build the Hamiltonian. I build the Hamiltonian with Rabi frequency, raising up, lowering operators. I have thrown away the unnecessary parts of the thing, which is basically the sigma z one, because now I'm already in the excited state. Forget about it. I need to define my collapse operator or my Lindblad operator. My Lindblad operator comes from this square root of decay rate multiplied by lowering operator. Is how we defined it. Right? That's a Lindblad operator. What is my observable that I'm interested in? Excited state population. Observable is excited state population. You agree? This excited state population. Right? Good. Now the great thing about Q-tip is what I have written, all the equations and stuff like that. We don't need to care about it. We take this Hamiltonian, the initial state, the time grid, your collapse operators, and the observable, put it all into this magic master equation solver, Lindblad master equation solver, and you'll get result. Spectacular. I don't need a theorist. I can do all kind of theory myself. I'm sorry, Krishna. No, but you have to be very careful of defining the correct Hamiltonian, correct initial state. It is easier said than done. Okay, and then we'll plot the results. If I plot this, you'll start seeing this. So when I have gamma much smaller, my Rabi frequency much smaller than gamma, you have an exponential decay. Right? When I have on the other end, where my Rabi frequency much larger, you see very rapid oscillations, which also decay, but they're kind of oscillating. Very fast frequency. Now in between, you have something in between. Right? Now I want you to kind of take time and kind of think about the physicality of what this is. You have some question?
Steady state population there. I was thinking they should be all in the same value, but here for the past
It's just normalized at the end. And it's the relative amplitudes to begin with is some kind of normalized thing.
What is normalized?
I mean, it's just starting from 1 and it's decaying.
Yeah, but in the oscillatory case,
Uh-huh.
the steady state population at the
It will be somewhere in the middle, right? At 4.5 or something.
yeah, but the in the fast decay rate, that is not going till 0 or even at some other value, let's say 50% or something.
Yeah, because of I don't know the choice of gamma that I used. We can evaluate that by changing gamma and see how that changes. That can be an evaluation that you can do, for example. Kind of take different gammas and see how this rate changes. By changing gamma, that rate should change. Right?
But all the three cups are using the same gum.
Same gamma, but different
Rabi.
Rabi. Different Rabi. That's important. It's a combination of both. That's exactly the point that I'm trying to drive, is that when you think excited state population lifetime, you always think, oh, it's coming down. It also depends on how much I'm driving. What is the strength of light matter? Does it make sense? Or it doesn't? You're not convinced?
Means I was thinking like a simple harmonic oscillator. So
Yeah.
whatever with the damping, at last it will come to a means.
At some point, asymptotic limit.
Yeah.
I agree.
And
We have
in-
not reached asymptotic
Yeah,
limit.
even in all the cases, it will approach to a particular.
That's right.
Yeah, but
Yes.
here the steady state populations are different in 3 different.
It's not. That's what I'm trying to say. You need to wait for longer time. The
Oh,
time. You need to. I just calculated for finite time.
Okay.
You expand it at some point, asymptotic limit, it will come. It has to, right? Otherwise, it's meaningless. In this time window, it doesn't appear.
Okay.
Make sense?
Yeah.
Your question?
How do we think about the final excited state population in terms of omega and gamma? Like, what is the relation there? So you see 0.5 for the oscillating case,
Mhm.
but then how do you?
This is exactly what he is asking, in the sense that at some point, they'll asymptotically, all of them has to come to the same point.
Right, but why 0.5 or whatever that value?
I mean, at some point, they should all go to zero.
So eventually the final state should be zero.
It should be zero.
Okay, right.
They'll all be going to zero.
That was fine.
Because it cannot live there forever, right?
Yeah,
But it's exponential, which means it will never be zero. That's also
sure. But it should be zero. Like the expected final at t
Yes.
tends to infinity is zero.
Yes. Okay. So as you can see, it's kind of pretty elegant way of doing things. You can do exactly opposite. For example, I did it. Here I considered that I'm already having an excited state population and let it evolve. You could also do exactly opposite, where I assume that everything is in the ground state. Okay, so I have that as well. So this is simulation of two-level system with everything in ground state. Same parameters again. Of course, I used only one omega Rabi frequency. I didn't do anything. I did slightly differently here, lowering operator. There is a function called destroy. Just to show that there are multiple ways of defining lowering raising operators in QTIP. So you can define your sigma minus to be this. Here I wrote down the entire Hamiltonian, not just the decay part, but also the sigma z part. This is the same collapse operator. Density matrix, define it slightly different, but if you think carefully, it's again base is 2, but now I'm assuming everything is in the ground state. Right? Everything is in the ground state. I didn't explicitly write it out separately. Same thing, time evolution. Our beautiful master equation solver will do everything for us. We don't have to care anything. And you will see here, there is a rise time. Excited state population. You're going from the ground state to an excited state and then oscillate. Okay. Remember, I have not assumed any form for my driving resonance yet. My E of t is E of cos omega t still. It's just turning on at that point. Okay. So I have not introduced a delta function explicitly to capture an ultra short excitation. That we will do later on. I'm not that way. That might be a bit confusing for us, but you can see the rise of the population, and then it's oscillation. Now, if you change your Rabi frequency, this will change. Kind of expected. Okay. Now, I want you to kind of, we can have discussion about this, but I want you to first go implement these things. Try out everything. Try out all parameters. Change all parameters. And kind of make observations. Okay. And here we have plotted only excited state population. What if we start also bringing in coherence with appropriate collapse operators for decoherence or dephasing? I've kind of listed sort of an assignment which I'll send around at some point. could kind of take till end of the week. We don't. Shiva, is it okay? End of the week, we can kind of
Probably
Friday or
we can finish it on Friday so that we can maybe discuss on Saturday rather than.
so you could kind of go. I'm not explicitly discussing all possibilities here because Q-tip is so nice and elegant. I want you to really play around with it and kind of comment on what you think of it. Okay, so you can go and do all of this, and then we could have another discussion session. But as you can see, it's not complicated. Once you get the idea of how to write the equation of motion, right? Basically, you write a Hamiltonian, you define your collapse operators or dissipation terms, your Lindblad operators, right? Once you identify these two, put it in there in the MeSolve, and it will do. The only thing that you need to worry about, you need to define where your starting point is. Here, I'm starting either from the ground state or from the excited state. I could start somewhere in between, with half in the ground state, half in the excited state. We can kind of explore all kinds of possibilities. Okay? Fair enough? Okay, I think we can stop here because there's been a lot covered. I want you to kind of go over it, kind of understand all the implications of this and understand the power of Q-tip. And we will meet again tomorrow.